All right, good morning, everyone. So I'm here to tell you more about security models and so on. So Hugo yesterday gave you an overview over almost everything, which is good. And what I'm going to do is basically put it into the perspective of security models and security proofs, right? So you will see again, for example, the unknown key share or identity misbinding attack. And we'll see how it matches to what we define as the secure protocol and so on. So before I start, actually, I would like to know about your background. So let's say who has some bare knowledge about crypto and just knows what the difference between public key and secret key crypto is? Okay, a few. And it's the Bellare-Rogaway model. There's a joke in the key exchange community. There are more security models than there are key exchange protocols. So you'll see that we have plenty of models. They all have good things, bad things. Oh, I'm making the cameraman really nervous here. Sorry. Okay, and I picked this one because it's a very clean model, very simple, and then you can extend it from there. And once you understood the Bellare-Rogaway model, it's easy also for you to get into the other models. And I decided to split this into two parts. One is about passive adversaries, and the other one about active adversaries. So this will be the first two sessions. And by the way, the sessions are not really aligned to this 1 hour thing, so some of the topics are a little bit shorter, so I will just take 10 minutes from the other slot and shift around a bit, but roughly this is it for the first two sessions. And then I think according to the program I would talk about forward security, but I changed this slightly, so I'll then talk about TLS 1.3 and other protocols. Basically because forward security is again about security models, and I didn't want to have the first 3 lectures about models only. And then we'll talk about forward secrecy. And then lecture 5 is about, well, we can say the latest hype in key exchange, which is called zero round trip time. This is something where you, if you reconnect to a server, you can immediately establish another key. And this is something which influenced heavily, for example, the design of TLS 1.3. And then lecture 6 is about composition and things like the UC model, for example. But we'll also talk about composition of Bellare-Rogaway. Okay, anytime if you have questions, just raise your hand. I may repeat your question or your answer because I think you're not connected to a microphone and then it's not recorded. All right, so let's dive into it. We started the Bellare-Rogaway model. So here you see again the good old Diffie-Hellman key exchange. Right now you are already familiar with that, right? You have G to the X and G to the Y. And then once you have the key, you typically apply a key derivation function. So in this talk, because I talk about security models, I often just ignore this step and talk about security of this Diffie-Hellman value. There are some exceptions, but usually if you have a good Diffie-Hellman value and you run it through a key derivation function, the KDF is good, then the eventual key is also good. So in this first part, we'll talk about adversaries which are only passive, right? So they can observe the communication, but they cannot, for example, change this to some other value. Okay, so in this first session, we only talk about passive adversaries, no active adversaries. So when you talk about security models, there are two basic approaches, and you've seen them yesterday in Hugo's talk already. One is a game-based approach, and the Bellare-Rogaway model falls into this category. And the other one is the simulation-based approach. And we'll talk about this in in the last chapter 6. Now I should mention that tomorrow David is going to talk about, David is here, right? I saw him. Ah, there he is. David is going to talk about password-based key exchange. And just to make sure that it's clear that the model you use for security is independent of the question whether you use strong cryptographic keys or passwords with low entropy. You can have password-based schemes and security models in a game-based setting, and you can also do that in a simulation-based setting. So this is orthogonal to the question. Okay, so we'll talk about Bellare-Rogaway, game-based. And the first thing you have to understand is there's not the Bellare-Rogaway model. There are plenty of Bellare-Rogaway models. They all share, of course, the same idea and a lot of stuff about the security model. So here's how this thing evolved over time. So you see, we started Bellare-Rogaway were the first to output a security model for the two-party scenario, key exchange, sometimes now referred to as BR93 because it was published in 93. Sometimes people call it 94 because I think the print of these proceedings was in 94. So 93, 94 is essentially the same. Then in 95, Bellare-Rogaway came and proposed another security model, now this time for the three-party scenario. For example, for Kerberos, where you have another party, a trusted party, assisting you in establishing the key and authenticating the partner. And then there's the password-based scenario, where now David joined. And this is sometimes called the BPR00, because it was published in 2000. And typically, if people talk about the Bellare-Rogaway model, they mean this or this. And the differences are subtle. So if they talk about the Bellare-Rogaway model, that's fine. You have some basic understanding what they mean about this. Okay, here's what the basic property is, what you want. And Hugo had this yesterday. This is key. Sometimes it's called key indistinguishability. Sometimes it's called secrecy or key secrecy. So we have a passive adversary. So we see that here we have two honest parties communicating. And we denote the messages they exchange usually by the transcript of the execution. Right? This is just recording what has been sent, what has been received. And of course, this is over a public channel, so this is available to the adversary. So we give the transcript to the adversary, and then here's what we expect. So we say both parties have derived their key. It's typically the same key, right? For a good key exchange protocol, you expect that both honest parties, if they act honestly, they derive at the same key. And what we do is we flip a random bit. And then we set K0 to be the actual key, and K1 to be just a random string, completely independent of what has happened in the transcript. Think about, you run the protocol, you get the key, you throw it away, you pick a new fresh random value, and you just replace the key with this fresh value. And then we give, depending on the secret B, either the actual key or the random value to the adversary. And now the adversary's task is to predict our secret bit B. Right? So it's going to output a bit. This is a bit. And we say the adversary wins if it is able to predict our secret bit. And then we can define, and this is not the last statement, how you define security of key exchange in this lecture series. Then we say the key exchange is secure against passive adversaries if, for any adversary running in polynomial time, the probability that A correctly predicts our secret bit B is at most a half plus negligible. If you don't know what negligible is, just think of this as essentially 0, or it's too small to matter. Okay, first question. Why don't we just say, for example, the adversary outputs the key. So we're not giving it this key, we're giving it the transcript, and the task of the adversary is to output the key, and then we expect the probability that A outputs the key should be negligible. Why don't we do this? Right? I mean, definitions, Hugo said, the definitions can be wrong. For some reason, people chose this definition saying, okay, you can't distinguish the key from random. Why not say you cannot recover the key? Say it again? Because we want no information to leak about the key. Yeah, but I could argue that, and of course I'm wrong, I could argue that if you cannot output the key, that means you miss information about the key. Sorry? Exactly, outputting a partial key is bad. So we had this yesterday, also in Hugo's talks. So let's say the key is compromised of a MAC key together with an encryption key. Okay, and then once you have the key, right, this is your key exchange, you use it in a secure channel. Right, so every message which is sent through this channel is, let's say, encrypted under the key. And then I hope you know that MAC then encrypt then MAC is better. And then you MAC the ciphertext. So if the adversary just is able, so if in my stipulation, the adversary is not able to recover the entire key, but it may happen exactly what you said, right? For example, I may be able to recover the encryption part and completely lack knowledge about this MAC part. So what this means is if I'm an adversary and I'm able to just get the encryption key, I cannot send message on behalf of the client or server. But of course, I'm able to see, to decrypt what has been encrypted here. Okay, so this is why we really want to have that the key is almost random. In particular, this means you cannot even compute a single bit of the key with high probability, right? Because even if you could compute a single bit of the key, you could easily distinguish it from random. Let's say it's the first bit of k, right? And I know this bit. Then for a random string, so I can output this always. And for a random string, I have a probability of a half to have the same bit or not. This means I cannot even recover a single bit. Okay, so this is the appropriate notion. To have strong security, to have a key. Hugo has a question? An answer?
No, I just want to say that you can think of a situation where the key that you use it as a one-time hack.
Yeah.
Just to send a message or zeros or all ones. That's a single bit.
Yeah, you had this example with the one-time pad yesterday. Yeah. Yeah. Okay, so we want to have strong security, which means that we want to have the key looks random. And this is basically how you formalize such things. If you think about encryption schemes, there you have the same. You basically have a secret bit, and you either send the left or right message, and you cannot tell which of the two messages it is. It doesn't mean you cannot recover, or it particularly means you cannot recover the entire message, but it actually gives you more security. Okay, so it is convenient to make this a little bit more formal and just say the adversary gets an oracle. Think of this as a box, right? And it can push a button. This is this here. And then it gets the transcript. This is called the exec oracle or exec box because it just runs an execution of the protocol and returns the transcript. And then the adversary can push another button, and then it gets either the actual key or the random string. And this box or this oracle has a secret bit be embedded into it. Now, in terms of formalism, you can do this as so-called oracle Turing machines, right? So you can say you have an adversary which has access to an oracle, or two oracles, and so on. I'm not going to do this, right? So you can all base it down on a level of Turing machines if you like. I'm going to stick to this visual interpretation of this with the boxes. Okay, so let's say we're fine with this model, right? Let's say, okay, looks good, I see a transcript, and I'm not supposed to compute any bit about the key. So let's say you have a protocol where both parties actually use static Diffie-Hellman keys. Okay, so they have built in some x and some g to the x, and every time they want to do a key exchange, they will just resend the same g to the x. And this guy, of course, then g to the y. Is this a good protocol? What was that? No. Why?
Because you'll have the same key.
Same key. Sounds wrong, right? Having the same key all the time, maybe not a good idea. But I should mention that sometimes you really have static Diffie-Hellman keys. For example, if you have certified keys on smart cards and so on, then they sometimes use static keys, but typically just one side of the two partners. Okay. Elaborate on. Why is it a bad idea? Because, okay, so what's going to happen is that this guy and this guy have the same key. So if they meet again tomorrow, they're going to have the same key again, and so on. And intuitively, what you want is every time I talk to someone, I want to establish a fresh key, right? I don't want to use the same key as yesterday. Otherwise, we can just switch. Otherwise, we can just switch to a shared key setting anyway, right? We can establish a key once and then just use that key, for example.
But I could imagine a situation that you cannot hold zillions of keys, but you can hold your g to the y, and then every time you actually recreate this constant shared key.
Enable replay discussions.
Should swap this. Okay, so this means then the adversary pushes the button again, gets either g to the xy or gets a g to the z. And according to the DDH assumption, it cannot distinguish the two cases. So the probability that A equals B here is really close to the guessing probability of a half. Okay. So we need to extend the model. That's what it says, right? If we're not happy with the protocol as is, and it's secure in the model, then there's something wrong with the model. The solution is easy, right? We just say instead of being able to see one transcript, we allow the adversary to do this multiple times. Can push the button, gets a transcript. Can push the button again, gets a transcript. Can even intervene this with this test query. So it can push a button, gets a transcript, push a button again, and so on, then make a test, then push the execution button again, and so on. So in the model, this causes some administrative overhead, because now we need to be able to say, okay, the adversary wants to test one of the keys in one of the executions. So we need to be able that the adversary tells me, oh, I want to see the key, or I want to test the key of the second execution. This is why we introduce some administrative identity. We can just think of this that the exec box or oracle just picks in the fresh identity each time it gets called. And now we give it the transcript and attach the identity. So this means if the adversary laser wants to test the second session, it will just say, okay, here's identity number 2, give me the key or a random value of that session. Okay? Purely syntactical to administer the different executions. Okay, so fine. Thing is, our protocol, which we just had with the static Diffie-Hellman keys, is still secure. Why? Because I push the button, And I get G to the X, G to the Y, and some identity. I push the button again get G to the X, G to the Y, and some fresh identity. I push the button once more, G to the X, G to the Y, and another identity. And in all cases, and then I can pick one of those, but the task is still to distinguish the G to the X from the G to the Z from a random string. So the problem, and maybe this now answers your question. So the problem is, typically a cryptographic key is used somewhere. So let's say you use this key here to establish a channel. Now for some reason you picked a bad channel protocol. It's really, really bad in the sense that it completely leaks your key, the entire key. Such a bad protocol. Okay? So this means if the adversary now observes the usage of this key here, then it gets to see the key. And what this affects is that it also knows the key which is used here. And maybe here you use it for, let's say, authentication, right? Entering a building and you just do a challenge response protocol with the key. Then this means, although this protocol may be secure, let's say you pick the perfect protocol, unbreakable, the fact that this protocol here is insecure also affects this protocol here. Because now I have the key, I can go to the door and just pretend to be the client. And this is what we don't currently have in the model. And this is why we're going to add something to the model. And these are the so-called reveal queries. We're going to allow the adversary to see some of the keys. Okay? And the reveal oracle basically models this bad usage of the key. Let's say you have a channel protocol which is really, really bad, leaks the key or parts of the key. And now we capture this in the model by saying, okay, the adversary can just press the reveal button or send some identifier to the reveal oracle, and in return gets the actual session key from that session. And of course, you can do it multiple times. So what's with our protocol now? Is it still secure? There was a no somewhere. Why not? Exactly. Let's say you're trying to distinguish, no, that was my, sorry. You're trying to distinguish this key, right? This was the door opening key. And I'm just trying to even distinguish it from random. It's not about recovering, it's just distinguishing it from random. So what I can do is I make a reveal query to that session here. So this gives me the key, right? Just as the bad usage in the channel protocol gives me the key. So now I have formalized this in a kind of oracle manner. So I have the key, then I'm going to test this. Now I'm getting the same key again, right? Because it's static Diffie-Hellman. So I have the same key. Or I'm getting a random value. And what I can do is I just compare, right? So this is the true key, right? I can always get the true key from a reveal. And in the test station, I get the actual key or a random value. So if it's the same key, then I know that I'm getting this. And this means I know that the secret bit is 0. And if I get a random key, then most likely they will not match. Right, the key and the random independent string, yeah, there's a small probability that they would match 2 to the, I don't know, minus 256, but you can neglect that. So this means with this reveal now, we have declared the former protocol as insecure. And maybe this answers your question now, right? Having the same key in different executions, shaky thing. You don't want to do that in crypto. Done. So this is the definition of passive security. Okay, so we've just identified the one with the static Diffie-Hellman keys as insecure. Can you give me any secure protocol in this model? No? Why not?
You can test something you revealed.
Exactly. So there's currently no. So I can just do the following, right? So I'm running an execution. My laptop. So I'm getting the key here. I'm the adversary. Right? So I'm going to ask to test this. Okay, so I get either K or a random string. And then I'm going to reveal the same session. Sorry, should say execution. Not at sessions yet. And the reveal gives me the key. And then we have the same problem we just had before, right? It's easy for me to say, oh, this key, this one is random or not.
I was thinking that in reveal, you reveal for other IDs, not the ones that you
You would reveal for other IDs, exactly. That's what you want, right? So right now, this is a kind of trivial attack. I'm asking you, is this key secure? Or I'm asking you, can you tell me something about the key? And by the way, here's the key. There's nothing to protect here, right? Cryptographically, there's nothing you can do about this. Okay, so we need to add something, and this means that the requirement here is the following, the one down here. The stipulation is that the adversary only wins if it A, predicts the bit B correctly, and B, if it does not make a test and reveal on the same execution. Right? So every identity asked here must be distinct from the identity asked in the test session. So this means this attack is no longer allowed. Second. Well, if we talk about, if we talk about this protocol, this is still okay, right? Because this has, let's say, identity, this has identity 1, and this has identity 2. So I can make a reveal on an identity 2, I can make a test on an identity 1. That's fine. Okay, there was a question in the back. What's the difference between test and reveal? Think about reveal as basically leakage of your key through some bad usage. And test is basically saying, this key still looks good to an outsider, to the adversary. Right? This is like the intuitive explanation. If you want to talk about the model, you see here you either get the actual key or a random key. Your task is to decide which case it is. Right? And reveal always gives you the exact session key. Yes. We just added the possibility for the adversary to say, hey, this key from another session is leaked, and I can use that to break the security of the other key in another session. That's what it says.
So why do we need that the adversary doesn't ask the test?
Say it again, why the adversary?
Hasn't applied the test. You say you know.
This?
Yeah. You say it hasn't asked test, and why not?
It means that you cannot ask test and reveal about the same identity. Maybe it's ambiguous formulation, I don't know. So it basically says you cannot use, think of this, they must always be different. This is the technical stipulation. How many times can we ask for the test, Oracle? Give me a couple of more slides and I'll get back to that. It's a tricky question. Yeah, I was expecting this, very good. I was expecting this that, yeah, we said you can ask multiple, you can see multiple transcripts, you can ask multiple reveals. Short answer, most of the times it doesn't matter. There's very few artificial examples where it makes a difference if you have multiple test queries or a single one. Actually, for David's talk about password-based, there's a big difference. In general, if you talk about strong cryptographic keys, doesn't matter a lot. But I'll get back to that. Okay, so this is this additional stipulation of saying, okay, you cannot mount trivial attacks, right? Like test something and reveal it. This is usually called the freshness condition. Some papers you also find it as kind of cleanness condition, but most people would use freshness. Freshness means that the test session is still okay. There's no trivial thing you can do to break indistinguishability for the test session. So later when I talk about freshness, there's always some condition. The thing is, we'll see, for example, in the active cases, basically the outset here remains. Also the fact that the adversary has to predict a bit. And typically what's changing is this freshness condition. Do other stipulations to prevent trivial attacks. Okay, so let's look at the plain Diffie-Hellman. This is one of the steps where we're going to do a proof. So intuitively, what we expect, we're talking about passive adversaries here, right? So no adversary is sitting here and changing this information. So intuitively, we would expect that this is a good protocol. One party sends something, the other one sends something, the adversary should not be able to recover the key. And then we should also be able to prove it in the model that I just proposed to you. Under some cryptographic assumption, and the assumption is again that if you have G to the H, G to the B, and G to the AB, then this is indistinguishable from a tuple of 3 random group elements. So we're going to do this now. Going to prove this. It's kind of to get into the model and also into the proving stuff. I have it on slides for your convenience, but let's do it on paperwork. Okay, so we're going to simplify a little bit in the proof. I'm going to skip over some technicalities which block the view on the important stuff. Cameraman gave up on following me, so it okay, so let's say we have an adversary. And let's say the adversary runs 3 sessions, right? You can generalize this arbitrarily to Q sessions. For now, we just say it runs 3 sessions. And let's say it first runs the the executions. So it's going to run execution 1 time, another time, and another time. Each time it gets a transcript. Okay, so this would be ID, let's say 1. And the transcript would be, should be G to the X1, G to the Y1. Hope it's still readable. So this ID would be 2, G to the X2, G to the Y2. Right, this is the transcript. Now we're not talking about static Diffie-Hellman anymore. We have fresh random values each time we execute. Right? So x1, and x2 and so on are all independent. And we have ID3 giving you G to the X3, G to the Y3. Okay, so let's say the adversary will test so let's say we know the adversary is going to test session number 2. And in order to enhance its chances to predict a bit, it will make a reveal on identity number 1. Right? This is admissible. It's a different identity. It gets the key, which in this case is G to the X1, G to the Y1. Right? I'm ignoring a key derivation function. I'm just talking about the plain Diffie-Hellman keys. Okay? And then it's going to make a reveal on ID number 3. Right? And it's going to test. Let's say the adversary does this at the very end. It's going to test session number 2. So now it's getting K I should say it's getting G to the X2, Y2, or a random group element. Okay? So here I make the assumption that we know that the adversary is going to test session number 2. What if we don't know this in advance? Maybe the adversary decides on the fly. While seeing some of the revealed keys, it says, oh, okay, now I'm going to test the other session. How do we deal with this? Any idea? Does it matter? It may, because the adversary may really choose. It matters for the reduction. The adversary may really choose on the fly, saying, "Okay, I've seen keys of session number of execution number 1 and 3, or number 1, and now I see that maybe session number 2 is more vulnerable than number 3." Could be. Who knows? How do you predict something which you don't know? Guess. You just pick one of the executions as random, right? We know it's going to be 3 executions or Q executions. We're just going to guess in advance, oh, I think the adversary is going with number 2. So that will lose you a factor of 1 over Q in your success probability, but typically the number of executions is polynomially bounded, so this hurts a little bit, but not too much. Okay, so we can just think that we know which session is going to be tested by guessing in advance. Okay.
If you could test many sessions, but they all had the same B, then you wouldn't be able to do it.
If we can test many sessions, then it gets much more complicated. Yes, we'll get to that. For now, we just have one possibility to test. Okay, so now our task is we want to show if this adversary breaks the key exchange protocol according to our definition, right? So it can predict the bit and it does not violate freshness. And our adversary in this example doesn't violate freshness. Then, let's call this A, then we can define an algorithm B who breaks DDH assumption, right? And this is the reduction we want to do. Right, because vice versa, it means that since we assume DDH is secure, there cannot be such an adversary B. And if there's no such adversary B, it means that A cannot exist. Okay, let's do this for our specific adversary. Okay, so here's our adversary, A. There's some exec, reveal. So this is for number 1, this is for number 3, and then does the test. Okay, we're going to give our reduction. The reduction is just going to run a simulation of this adversary in all the environment. Right, so this will be our overall algorithm B. And this algorithm B gets as input, should have been shorter on, something G to the A, G to the B, and some G to the C, where C is either A times B or it's random. Right, this is a DDH tuple I get as input, and I'm supposed to decide if it's random or not. So what we're going to do is B is going to simulate the first execution for identity 1. It's going to pick x1 and y1 and returns g to the x1, g to the y1 to the adversary. Right? This is simulation. I have full control over the execution box. I can just replace it by my own computations. And I'm going to do the same here. Right? This is execution number 3. And I know in advance, because I've guessed, I've predicted, that test station number 2 is the one the adversary is interested in. So what I'm going to do is I'm going to use G to the A, pretending that the client has sent G to the A, and the server has sent G to the B. Okay, I don't know A and B, small a and b, because I just know this g to the a and g to the b, but it doesn't matter, right? I'm just supposed to provide a transcript. And that's perfectly legit, because g to the a and g to the b is like a Diffie-Hellman key exchange. Okay, so what happens if the adversary now asks for revealing identity number 1? How am I supposed to answer this? Say it again? Exactly. I've picked x1 and y1 myself, so I can return g to the x1, y1 easily, right? And this is the correct key. The adversary expects me to give the key from that session. Here's the key. And the same, of course, here. Right? I can return g to the x3, y3. So now the adversary makes the test query. What am I going to do? J to the C, exactly. I'm going to return J to the C. At this point, I don't have any information about whether C is the actual Diffie-Hellman key or if it's a random group element. But it doesn't matter, because I'm going to return this, and then the adversary is going to make all the work for me. It will tell me if this key is the actual key, G to the AB, or if it's random. So what I can just do is, I'm just going to copy this output bit as my prediction for the DDH case. And then you see if the adversary is able, our adversary doesn't break freshness, right? We just ask a task for a session for an execution which is not revealed. And if the adversary predicts the bit in the key exchange protocol, then it does so in this simulation here. And if it predicts correctly, then I'm going to break DDH. I can distinguish the two cases. Okay, that's good. Because it means that the protocol is secure against passive adversary. This is what we expect. It matches our model. And for example, the one with the static Diffie-Hellman keys we have identified as insecure. Here's a question. I'm going to modify the protocol slightly. Okay? Okay, so this guy is, I don't know whoever started. This guy sends G to the X. This guy sends G to the Y. And now what I'm going to do is I'm going to compute the key as before. Maybe run it through a key derivation function, right? I'm going to step over that. And now what I do is I'm computing a MAC for the key over the transcript. Okay? So we've seen yesterday this a couple of times, that you sign the transcript in order to authenticate and so on. So what do you think of this protocol? It's not good? Say it again, because you can MAC? Ah, exactly, yeah. You can break it. I mean, according to the model. And you've given the hint. The hint is, I'm going to use this as my test session, right? So now, okay, so first I run this thing, I get an execution which gives me the transcript, which is G to the X, G to the Y, and now the MAC, tau. And then I'm going to test the exact session. This is fine, right? Because I haven't revealed any session, so I'm still not violating the freshness condition. I can do that. And now, you hinted it, what I'm going to do is this gives me either K or a random string. And now what I'm just going to do is I'm going to check if tau equals the MAC of, let's call this K bar, G to the X, G to the Y. or strictly speaking, I verify the MAC, but let's say it's a deterministic MAC and I verify by recomputing it. Now, for the actual key, equality will hold, of course, right? If I get the right key here, I'm just recomputing the MAC for the right key so I can check that this is true. For a random key, most likely the equality will not hold. There's a small probability, of course, that you can forge a MAC or guess the key, but essentially it will not hold. So this attack tells me I can distinguish the two cases, B equals 0 or B equals 1. Okay, so we can break, so according to our model, this protocol is insecure. Can you break it in practice? Depends on how hard it is to calculate the MAC. Let's say it's a secure MAC, HMAC.
Depends what it means to break it in practice.
Yes, depending on the
Let's say complete break, recover the key. What's that? Very low chance. Right. There's no obvious attack to it. Let's put it this way, right? Our model says this is not good. This is insecure.
But that's also true if you reveal half of the bits of key.
Say it again. That's also true if you reveal half of the bits off.
Instead of MAC, you just reveal half of the bits of key.
Yeah.
You cannot find the original key, but you're convinced that if this is not related.
Yeah. The reason why I'm bringing this example, this is what TLS 1.2 does. And Kenny will talk more about TLS 1.2. Actually, I'm just talking about TLS 1.3, the latest version. TLS 1.2 does this. They exchange keys, and then they use the key in a so-called finished message to authenticate with the MAC. They use the key which has been derived. Now this has changed, luckily, with TLS 1.3. They basically separate. There's also a finished message and a MAC, but this is a separate key. And from my experience, it's tough to explain to practitioners why this shouldn't be a good protocol, right? Because it's in the gray zone between provably secure and completely unbreakable. Hugo was first.
So I think that in TLS itself, this has not broken TLS as a full protocol that includes this and the record layer. But if you think about this protocol as a generic protocol, and it makes sense to think about TLS as a generic protocol because there are many applications that can just take the TLS handshake as their own key exchange and then do something different.
Yeah. So Hugo's remark was it has not broken TLS 1.2. I mean, this point has not caused any trouble with TLS 1.2, at least not in practice. It's true, absolutely true. It gave us a headache in order, if you want to prove something about TLS 1.2 in this Bellare-Rogaway style. So you can think, I mean, one of the problems you see, and this is what Hugo mentioned, is that let's say you compose this with a stupid protocol, right? So I'm going to remove all this. So let's say this finishes your key exchange, and now the protocol is send me a MAC. I can send you a nonce, or no, well, just send me a MAC over for the key over g to the x, g to the y. This means now the protocol, the subsequent protocol, of course, this is badly interwoven with the key exchange protocol, but it's not clear how the MAC is used subsequently, how the key is used subsequently. And if it's somehow also used in the MAC, you need to be careful that the MAC usage in the following protocol, let's say this is the channel protocol, does not intervene badly with the key exchange step. And I've had this discussion because then practitioners said, okay, but I'm going to use a counter and I'm going to use a MAC of 0 here, and subsequently I increase the counter every time. So the first message here is going to have a MAC K and 1 and whatever it's following. Right, so they kind of separated. Again, this is a tough case. As one working on analyzing key exchange protocol, I'm very happy that TLS 1.3 has gotten rid of this and now uses keys, kind of independent keys for the channel or subsequent protocol and in the key exchange protocol. Okay, I have something for the break, but okay, so far for the passive adversaries. Now you should have a basic understanding what's happening there, how we model stuff, and what are good protocols and what are not so good protocols, and so on. So I'm going to use the last few minutes to start about the active adversaries. So now the change is, this is sometimes also called the $VIU adversary, that this guy has full control over the network. So it may start stepping in halfway through the protocol. This is the example here, right? Client and server start communicating, and then the adversary just takes over. Jams this client or disconnects it, whatever, and from then on communicates with the server on behalf of the client. It may also be that it just injects a message here, so it intercepts the message, stops it, and injects its own message. A very bad thing which could happen is the adversary may even start as the client. Right, let's say this has a few more rounds. Then it may surprisingly be able to connect the client. The client says, yeah, there's a key exchange protocol running. I think I missed the first two messages, but I don't mind. I'll just step in at message number 3 and continue. It's a bad thing, right? You don't want to happen. Don't want to have this happen. Okay, so the first thing we need to talk about is, if we talk about active adversaries, is identities. And this is a must, because if you think about our previous protocol, the basic Diffie-Hellman protocol, we had the client pick some G to the X and send it, and then receiving them G to the Y. So from the server's perspective, it cannot distinguish the case that the client sends this value or the adversary. Just receives some G to the X, has no idea who the author of that message is. So what we need to have are identities, right? Because it makes a big difference. If it's the client communicating with us, we expect this key, unless the adversary tampers with the messages, we expect this key to be good. If it's the adversary talking to us, this key from our perspective is not good, right? Because the adversary may just simply know the key of on the server side. Okay, and what I'll do in this talk throughout, and what you find very often in the literature, is you just assume that everyone has a certified public key. That's the typical mean for setting identities. And certified meaning, of course, that you cannot forge, you cannot pretend to be something else just by using another person's public key. And then what you do is, in the key exchange, you output the key in the end. Okay, so in this maybe, let's say, a signature key or an encryption key, and then of course you hold the corresponding secret key as well on both sides. And now what you do is, in the end, you not only output the session key, but you also output the partner identity. Basically saying, oh, I think I'm talking to Amazon, right? So something we don't consider here in this talk, after the break, is we do not talk about revocation of keys and certificates. Now, this is, of course, a big gap between practice and theory. In practice, you want to be able to say, my key has been corrupted, and I need to revoke the certificate. This, of course, affects also security issues, but most of the key exchange protocols and models just say, they are keys, they're there forever. They don't get revoked. There are approaches to incorporate revocation and things like this, but then it gets even more heavy. I'm not going to do this here. We're going to stick to the assumption that you get your key certified once, and the key is good, except for corruption, see later. The key is good for the rest of your lifetime. And what we don't consider either... Sorry?
Beforehand, you didn't like the idea of having the same key.
I didn't like the idea of having the same key as a kind of in the execution. Right now, I'm talking about the key which you use throughout executions, but now you need to do it in a careful and clever way in order to avoid the things. So we'll get to that. It's not like sending this public key only. And something we also don't consider here is that the adversary registers keys. Right now, you assume every party is initially honest, gets a public key, which is somehow generated by the users themselves or by some trusted party. They are certified, and that's it. Most of the protocols I know would still be secure if the adversary can register keys, but we don't consider this here. We assume all the keys are generated, and then the adversary gets to see the public keys. Okay, let me see. Yeah, maybe I'm going to do this after the break, but just for the break, if you want to think about something during the break, instead of talking to your fellows, here's something. So I said that a key exchange is BR secure against passive adversaries. We're still now in the passive setting. If the probability that the adversary wins is at most a half plus something you can neglect. So very often, for example, what you find in encryption is that you can just say that, oh, it is bounded from a half, either on the positive or negative side by something which is negligible. You can do this, for example, if you talk about security of encryption scheme. So here's the question. Can you do the same for key exchange? And if you want to have a reference to a model, would be that one, right?